Hi everyone, I'm Saranya Anantapantula, and recently, in February 22nd, in 2023, I flew down to New Orleans in order to attend and present at the World Aquaculture Society Conference. I learned a lot from talking to the farmers and aquatic researchers in the conference, attending presentations, and learning about various engineering tools used in aquaculture from various companies. I presented my research that I had started in 2020 on a meta-analysis on the effects of various algal bloom control treatments, and my presentation won the first place oral presentation award winner with a reward of $1,000. If you have any questions, feel free to ask them in the comments. Without further ado, here is my presentation, and I hope you enjoy.
School, working with Alan Wilson from Auburn University. And so she's our first presenter, so I'll turn it over. Go ahead.
Wonderful. Hi everyone, I'm Saranya Anantapantula. I'm a junior at Springford High School, and today I want to talk about a meta-analysis on the effects of various algal control treatments on controlling algal blooms. This is a project I worked on with Dr. Alan Wilson from Auburn University. So firstly, algal blooms form in fresh water, specifically in water bodies that are used for drinking water, recreation, and aquaculture. This photo in particular was taken in a catfish aquaculture pond in West Alabama in the summer of 2021. So primarily, algal blooms form because of excessive nutrients that enter the water, such as nitrogen and phosphorus from fish feed and fertilizers. In aquaculture, because we have fish feed directly into the water, the nutrients from that fish feed is loaded directly into the water, which makes it very likely for algal blooms to form. So out of all the algal blooms that form, cyanobacteria blooms, or blue-green algae blooms, are the most harmful to water quality. They can produce toxins such as microcystins, which can harm aquatic animals like fish, livestock, pets, and even humans at really high concentrations. Also, when the algae dies, bacteria breaks it down, and this process uses up oxygen. Oxygen is then depleted from the water, which results in fish being suffocated and dying. Cyanobacteria can also produce compounds that make the water taste and smell bad. This results in the fish tasting and smelling bad, which can also cause the fish to have a reduce in consumer demand. And then there is a reduce in how much money is earned from that fish harvest. So because algal blooms are extremely harmful to the environment and the economy, we commonly use algal bloom control treatments, such as bacterial, physical, chemical, or plant-based treatments. In aquaculture in particular, we use chemicals like copper sulfate and hydrogen peroxide in order to control the algae. So in current literature, there's a problem. There's lots of variation between different research studies of the same treatment. There's also lots of variation between various treatments. And this makes it incredibly hard to decide which treatment to actually use. So in our project, we wanted to counter these two problems. So in order to best support water management practices, we wanted to quantitatively synthesize all available data about the effects of previously used algal bloom control treatments in the field. So in order to do this, we used a meta-analysis, which is a quantitative synthesis of literature. Our meta-analysis provided objective results regarding the effect of various treatments and gave us a way to compare the effects of different treatments. So in order to find literature that would help us do this, we searched in the databases of Web of Science, Aquatic Science and Fisheries, and CAB abstracts. To search, we used keywords, all possible variations of the words relating to algae, treatments, field experiments, and fresh water. Then, once we found some abstracts, we had to decide would it be relevant to include in our meta-analysis or not. And in order to do this, we used search criteria, some of which were making sure that the experiments were conducted in the field, because that's where algae naturally form. The other one was making sure that we had water quality data relating to algal bloom abundance, as that's what we were focusing on. In the end, we had 39 papers to use for our meta-analysis. So from those papers, we collected data from the figures and tables, specifically relating to the mean response, the error measurements, and we converted all of them to standard deviation, the sample size or the number of replicates the treatment group or control group had, the time the sample was collected or how many days after the treatment was added, the treatment name, and also the treatment group. So chemical, bacterial, physical, or plant-based treatments. And then what was that data collecting? What was that data on? So it was the response type, which we put into 4 bins: pigments, cell density, toxins, and off flavors. Once we collected this data, we made all the units the same in each of those 4 bins, and then we used treatment name, treatment group, and response type for further analysis. So we analyzed our data using effect sizes, specifically the natural log response ratio. You can see the formula on the slide. The natural log response ratio essentially compares the treatment group to the control group. If there is a negative effect size, that means that the treatment was effective at controlling the algae. On the other hand, if there was a positive effect size, that means the treatment was actually ineffective. Moreover, the magnitude of the effect size indicates how impactful that treatment's effect was. So if I have a really negative effect size, that means that treatment was very beneficial at improving the water quality. So after we collected our data and calculated effect sizes, we had this big data set of these effect sizes and variables. And then we split that data set into 2. The first data set was the most effective day data set, which included the day of the experiment that had the most negative effect size. We also had the end of experiment data set, which included the last day of each experiment. In total, both of these data sets had 227 different types of data, because there was 227 experiments that we collected in our literature search. So in order to visually represent our data and data analysis, we used orchard plots. So the individual effect sizes are shown in the lightly colored data points in the background. The mean effect is that bolded data point in the center. The 95% confidence intervals are the thick lines around it, and they determine significance. And then the thin lines are the 95% prediction intervals. The size of the bubbles relates to how much precision that data has. So as expected, on the most effective day, the mean effect was very negative. But it was surprising that it was much more negative than the mean effect of the end of the experiment. So this change over time may be because when the most effective day happens right after the treatment is added. But over time, that treatment's effect may have worn off over time, and then by the end of the experiment, that treatment is not as effective, resulting in a much less significant effect of the treatment. So this change over time actually shows how important time is to consider when looking at a treatment's overall effectiveness, and also suggests that these treatments' effect may be short-lived. So because our data set had many different types of variables, like the treatment information by treatment name and treatment group, and then response type, we analyzed these different variables. So first, the response types. On the most effective day, all response types were significantly reduced. But by the end of the experiment, cell density and off flavors were not significantly affected. You would expect that cell density and pigments would have similar effects as they measure 2 different aspects of the same thing, algae. But they do not, and that may be because cell density is not as frequently measured, as it is harder to do so, which results in more variance and then less significance. Nevertheless, the consistent change in effectiveness over time, as we saw on the last slide, shows that, again, time is really important to consider when looking at treatment, the longevity of using a treatment in long-term water quality management. So we also analyzed the different treatment groups. So first, the chemical treatments. Chemical treatments produced around 88% of the entire data set. So on the most effective day, the chemicals had significantly reduced all response types. And I'd like to remind you that these thin lines are the prediction intervals. The confidence intervals are the thicker lines, and they're quite hard to see because they're very small. But I assure you that's significant. So then by the end of the experiment, similar to our overall analysis, the chemical treatments did not significantly affect cell density and off flavors. So this overall change in effectiveness over time between the most effective day and the end of the experiment may be because chemicals can negatively impact zooplankton, and zooplankton eat the algae. So with the zooplankton gone, there's more algal growth closer to the end of the experiment, or closer to later in time after the treatment has been added, which results in a less significant effect of the treatment by the end of the experiment. So then bacterial treatments. On the most effective day, there is overall significant improvement in water quality, but by the end of the experiment, we don't see that significant improvement anymore. Similarly, with physical treatments, it effectively reduced algal growth and improved water quality on the most effective day. But by the end of the experiment, those effects were not long-lasting, and we don't see significant improvements in water quality. So only one experiment had actually used a plant-based treatment, which was barley straw. Although we do see a significant improvement in water quality on the most effective day, there's only one effect size, which makes it hard to actually make reliable conclusions. So clearly, more research needs to be conducted in order to make reliable conclusions. So then we did an individual treatment analysis. So out of all the 28 treatments that our meta-analysis covered, only 4 of them had effectively reduced algal growth or improved water quality on the most effective day. And all 4 of those were chemicals, but only 3 of them had actually held sustained effects until the end of the experiment. And those 3 were copper sulfate, hydrogen peroxide, and peracetic acid. Interestingly, one treatment had actually worsened water quality by the end of the experiment, dicot. And as for the other treatment groups, the bacterial, physical, and plant-based groups, we see that none of their individual treatments had significantly improved water quality. However, having limited available data made it challenging to actually see significant results. Moreover, only three combined treatments were tested, as you can see here. However, although they didn't show significant effects, combined treatments do show potential for being more cost-effective, eco-friendly, and potentially more impactful in the long run. But overall, our meta-analysis shows that we need to conduct more research on using sustainable treatments for controlling algal blooms in the long run. By sustainable, I mean being cost-effective and eco-friendly. So in conclusion, our meta-analysis showed that most algal bloom treatments were short-lived and ineffective. Moreover, the poor success of most treatments showed that these treatments the poor success of most treatments was surprising, given the frequent use of these treatments in water quality management and aquaculture. Out of all the 28 treatments we had tested, only 4 of them had shown significant effects in actually improving water quality. And these 4 treatments had primarily controlled the overall treatment effects. But in order to actually understand their effectiveness, we need to look at time as a variable, as that is essential for long-term water quality management. Lastly, our meta-analysis showed the need for more research, looking at more sustainable ways of treating harmful algal blooms. And with that, I'd like to thank the people who have helped us with our project, and thank you for your time and attention. I'd be happy to answer any questions.